Staring directly into the intense light of the sun triggers an automatic physical reflex that immediately forces the eyes to shut. For early astronomers in ancient Babylon and China, study was limited to moments when the atmosphere was thick with haze, or when a rare eclipse briefly dimmed the glare. This creates a difficult physical constraint. We are attempting to study a massive cosmic machine that destroys the very instruments and eyes used to observe it. The history of solar astronomy is defined by a series of technological workarounds designed to bypass the star's natural defenses. These centuries of effort have transformed the sun from an unknowable light in the sky into a laboratory for understanding how the stars in our universe actually function. By the 1600s, telescopes had arrived, but they initially made the sun more dangerous. The glass lenses gathered and magnified the intensity of the light, threatening to blind anyone who looked through them. Astronomers like Galileo and Christoph Scheiner solved the problem by projecting the sun's light through the telescope and onto a screen, creating a safe, indirect image. This projection method revealed dark blemishes drifting across the solar surface. Years later, George Ellery Hale used specialized equipment like this to prove these sunspots were actually sites of intense magnetic activity. Even with a clear view, the sun remained millions of miles away. There was no way to physically scoop up a sample of the star to identify its chemical components. In the 1800s, Pierre Janssen and Norman Lockyer used spectroscopy to split sunlight into a barcode of individual elements. Within that light barcode, they found a signature that did not match any element then known on Earth. They named it helium, after the Greek sun god Helios. Analyzing these spectral signatures allowed us to categorize the sun as a chemical entity with a measurable composition. There was another problem. The sun's surface is so bright that it masks its own outer atmosphere. This ghostly layer, the corona, remained hidden behind the star's primary glare. For centuries, astronomers had to haul heavy equipment to remote expedition sites, waiting for the moon to perfectly align and block the sun's core light. During an eclipse in 1919, the moon's shadow finally allowed astronomers to observe how starlight bent as it passed near the sun. This historic observation successfully confirmed Albert Einstein's early predictions regarding general relativity. In 1930, Bernard Lyot developed the Coronagraph to replicate this effect without a lunar alignment. A physical disk is placed inside the telescope to block the solar disk's primary light. With the main glare removed, the radiating structures of the corona become visible. The invention turned the study of the sun's atmosphere into a daily routine rather than a rare event. The final barrier was Earth's own atmosphere, which blocks much of the extreme ultraviolet light that reveals the sun's magnetic behavior. Scientists bypassed this by launching observatories into the vacuum of space, where they could monitor the sun's radiation without interference. Satellites like SOHO and the Solar Dynamics Observatory began providing high-resolution, uninterrupted views of the sun's activity in these ultraviolet wavelengths. By tracking these magnetic signatures over decades, scientists confirmed that sunspot activity rises and falls on a consistent 11-year cycle. Eventually, we moved from taking pictures to physical contact, building probes shielded against extreme heat to fly into the corona itself. In 2021 and 2024, the Parker Solar Probe executed passes through the multi-million-degree plasma of the outer solar atmosphere, the closest any human-made object has ever come to a star. At the same time, the solar orbiter moved out of the plane of the planets to capture the first images of the sun's mysterious south pole. Placing sensors outside of Earth's protective layers has provided a direct view of the star's chaotic, high-energy environment. Modern data reveals a star characterized by violent, churning magnetic activity. We can now see the physical consequences of this activity. In 1859, a massive solar flare known as the Carrington event triggered a geomagnetic storm that caused telegraph systems to fail and catch fire. Today, these observational tools serve as a critical warning system, identifying coronal mass ejections before they can damage the global electronics we rely on. Questions remain. Scientists are still working to understand exactly what triggers a flare to erupt and why the outer atmosphere is hundreds of times hotter than the surface below it. After centuries of workarounds, we have finally seen the sun, a beautiful,